Hello, in this video I want to look at Chapter 25, Sections 1 through 3, dealing with light and how light kind of interacts with different materials, whether it passes through or reflects off. For everything that we're going to talk about, we're going to think of light as a ray rather than a wave. Okay, so if we've got something here that the light's going to come in and hit, in actuality, we've got light coming in as a wave and then it bounces off as a wave. Okay, but that's hard to draw and hard to deal with. So typically we would just, as long as we're looking at kind of a bigger scale thing, we can consider it as just a ray coming in and then bouncing off. Okay, or a ray coming in and passing right through, rather than having to deal with it as a wave. It just makes makes all of the calculations a little bit easier. And as long as we're dealing with something that is significantly bigger than the wavelength of the light, it doesn't really matter much. We can think of it as a ray, and everything kind of works out for us. A couple of big terms that we need to cover here: reflection versus refraction. So in this picture from the text, we've got kind of the first case is the light coming from the sun to the earth. That would be just light in a vacuum, and so as light travels in a vacuum, it's really not having to interact with anything, and so it's not being changed, it's not being deflected at all. Once the light enters the atmosphere, then it kind of interacts with the air, and we get what's called refraction, where the light changes direction just a little bit, and we're going to call that kind of bending in quotation marks. It's maybe not technically correct, but we're going to talk about it because it just makes the most sense to say that the light rays bend as they pass through from vacuum into air, and then they're going to bend again when they go from air through glass or through water or anything like that. So that's refraction, which would be like the light coming through the window here. In this picture, though, we've got the light first kind of bouncing off the car, reflecting off the car, and so that's the difference between reflection and refraction. Reflection is where the light gets deflected and sent back off in a different direction. Refraction is where it passes through the material and only changes direction somewhat. And obviously there's going to be some overlap there where some of the light gets reflected and some passes through, but we're just going to be dealing with one or the other. We're going to consider it as either all of the light gets reflected or all of it gets passed through and refracted a little bit, just changes direction a little bit. So looking a little bit closer at reflection, it's kind of the easier of the two. So when we've got a light ray that comes in and gets reflected off of a surface, the angle is very easy to work out. Okay, this what's called the incident ray, where the light coming in, whatever angle that is from the perpendicular to the surface, it's going to reflect at exactly that same angle. Okay, so the incident ray is going to make the same angle with its perpendicular as the reflected ray is. Those angles are going to be the same for any reflected light, so that actually makes the calculation very easy. Okay, and you might be thinking of kind of a mirror here, but almost everything reflects light. Okay, just depending on how rough it is how much of a reflection you might see in that surface. So this is kind of an illustration of that. You can imagine, before we get to that, that if we had a mirror surface, we'd have all of these light rays coming in parallel, and then they would hit the mirror, and they would bounce off at that same angle, and then they would still be parallel. Okay, all of these light rays would come in, reflect off the mirror, and they would still be parallel to each other. Okay, that's not the case if we have more of a rough surface. Okay, the light rays will come in and then bounce off at perpendicular to kind of the tangent line at whatever that point is. Okay, because that perpendicular line is going to change depending on what the surface looks like. So all of these rays coming in are parallel, but then as they reflect, these all these lines perpendicular to the tangent line are kind of pointing in different directions. Okay, so we end up with all this light reflecting off in different directions. So that would be kind of something that's not very shiny. You'd be able to see it because all this light is reflecting off, but it wouldn't kind of reflect the image like a mirror does. Another example of that, we've got a sheet of paper here, and so if you're in a dark room shining a flashlight onto a sheet of paper, it doesn't matter who's standing around it, everybody's going to be able to read that paper, okay, because the paper is not perfectly smooth. It's not going to be like a mirror image off the paper, so that light is going to reflect at different angles. Okay, so everybody standing around is going to get some of that light, and they're going to be able to see what's on the paper. Okay, if you had something, say, written on a mirror in reflective paint, then, and you're in a dark room, only the person that is in line with that light, or roughly in line with that light, because nothing's perfect, only they're going to be able to read it. Somebody over here is not going to be able to read that because almost none of the light is getting reflected towards them. In a perfect scenario, none of the light is getting reflected towards them. Okay, so that's reflection. Refraction is a little bit trickier to deal with, and we've all experienced this. Okay, so if you're looking at a square tank like this, or sometimes even a glass of water that kind of has square edges, or a pool or whatever, sometimes you get kind of this duplicate image where the thing you're looking at is actually right behind the edge, and you can actually see two of them. And this is because of refraction. Okay, so first off, we'll just talk about what refraction is, and then we'll come back to the fish tank. If you've got this light ray coming in, and say we've got, doesn't really matter, but say it's air up here and water down here, when that light ray hits the water, it's going to bend a little bit. So it's going to be coming in at one angle, and in the water it's going to be traveling at a different angle to this perpendicular, the perpendicular from the dividing line between the air and the water. Okay, so the light's going to come in, hit the water, and actually bend a little bit. So that's why we can sometimes get this dual image here, okay, because the fish is right behind the corner, and so the light coming in the tank from all different directions actually has two paths that it can leave the tank at and still reflect back to your eyes. Okay, so it could come out here and bend this way, come to you, come out this way, and bend that way, and get to you. Either way, you're going to see the image. That's why sometimes you can see kind of a double image in water. Not a double image, but if you've ever looked at like a straw sticking in the water, or if you're standing in a swimming pool or whatever, a lot of times it looks like things are bent, like the straw would no longer be straight sticking in the water. That's just due to refraction. That refraction is all due to the change of the speed of light in whatever material it is. Okay, so what I've got here is the speed of light in a vacuum. So this is kind of our baseline measurement. If you're interested, you can look in the reading. They talk about how some early experiments that they were able to measure the speed of light. It's really pretty interesting what they were able to do with kind of limited technology. So this is the exact, or more exact, measurement for the speed of light. A lot of times we're just going to use 3.00 times 10 to the 8th meters per second, because that's accurate enough for almost everything we're going to do. So 3.00 times 10 to the 8th meters per second is what we're going to use for the speed of light. Now, that's in a vacuum, so when that light enters air, it actually slows down a little bit. When it enters water, it slows down even more, and if it enters something like plexiglass, it slows down even more. Okay, so depending on the material, the speed of light is going to change. Okay, some materials allow light to pass through without very much change, and some of them really slow it down. And we're not looking at kind of total internal reflection right now. We're just talking about the light that passes through, not the light that gets bounced around and reflected inside the material. So if we look at this formula here, it's called the index of refraction for any material. We can measure the speed of light in that material, and if we take the speed of light in a vacuum and divide by that, we get this index. Okay, so this has been measured for all sorts of materials. I just got some here in a table. So we can see that air, this index is really, really close to 1, which means that our speed was really, really close to the speed of light in a vacuum. So it didn't slow it down very much, and for most of our calculations, it's not going to matter at all, because that's 3 decimal places of zeros, so it's really, really close to the speed of light in a vacuum if we're just talking about air. Same with these other gases. Okay, get into liquids and it starts slowing down a little bit more, and in solids a little bit more still. Okay, so we're going to be able to use some of these values and this formula to do a few calculations here. So for this example, we would just want to find the speed of light in ethanol. So I've got the formula from before, and I looked up the index of refraction for ethanol from that table we just saw. So I can just plug into the formula here. I know the index is 1.361. I know the speed of light, 3.00 times 10 to the 8th. And I want to find the speed of light in the ethanol. So I just have to multiply that velocity across, divide by 1.361, and I can come up with my speed of light in ethanol. If I do that in the calculator, 3 times 10 to the 8th divided by 1.361, I should get 2.204 times 10 to the 8th. Okay, so a slower speed than it would be in vacuum. I should have meters per second on there. So it has slowed down, still going incredibly fast, but it has slowed down by, not quite a third. Okay. As we start talking about different materials and how light refracts in those materials, we've got this law of refraction, or Snell's law. And all that it says, just like before, we've got this light ray coming in, and then it bends a little bit as it enters the other medium. So this formula kind of governs those angles. If I've got my index for each material, the starting material and the ending material, or vice versa, then say this is the index for my starting material, then the angle of incidence goes here, and then the index for my other material goes here, and the angle of refraction goes here. And using this, I can plug in my knowns and figure out, say that I knew what both of the angles were, the angle of incidence and the angle of refraction. I could work backwards and find out what the index is. Or if I know both indices and one of the angles, I can find the other angle. So we'll see that in an example here. And it would be a good time to point out that if this is air and this is water, notice that this ray coming in, the angle of incidence is bigger than the angle of refraction is. If I come in and I slow down in a medium, then this angle actually gets closer to the perpendicular. If I come in and say I was going the other direction, if I was coming out of the water, and come out into the air, that angle gets bigger. Okay, so if I speed up, the angle gets bigger. If I slow down, the angle gets smaller. Alright, so another example here, I've kind of got it drawn out. I've got a beam of light traveling through the air and into a beaker of ethanol. Okay, this is ethanol. And the angle of incidence is 45 degrees. We want to figure out what this angle of refraction is. Okay, so from the table, we can get these indices that we need and just fill into the formula. So here I've got Snell's law, and I can just start filling in. So starting with the air, remember my index for air is basically 1. We're just going to use 1. And my angle of incidence is 45. My index of refraction for ethanol, I can look back at the table and get that, 1.361. And I want to find this angle. Okay, so I can do sine of 45, divide by 1.361, and I would get this big long decimal equal to sine of theta. I could do inverse sine on my calculator, and it'll give me an angle of 31.3 degrees. Okay, so my angle of refraction is 31.3, this angle here. We've gone from air into ethanol, which has a larger index, so it slowed down, that angle got smaller. Okay, came closer to the perpendicular. One more example here, very similar, only this time I know that we've got some unknown solid that we've submerged in water here, and we know what both angles are. We know what the angle of incidence is, we know what the angle of refraction is. We want to find the index for this unknown solid material. So just like before, we'll set it up, and we'll look at the table. The index for air, 1.333, sine of 20 equals this index that I don't know, the one I'm trying to find, times sine of 10. And I just need to solve this. So I'll divide by sine of 10, in my calculator, and kind of all in one step, I can type this in, divide by sine 10, and I get 2.63 for my index. Okay, so we asked the question, would it be reasonable to say that this unknown solid is actually quartz? If we look at our table, our index is 2.63. If we look at this table, quartz is 1.5. So no, definitely not quartz. That is far enough away that we can be pretty sure that it's not quartz. Okay, just depending on our experimental setup. But if we trust this number, definitely not quartz. Okay, so that's Snell's law. It's actually fairly simple to use. Plug in your knowns, figure out your unknown. Okay, and just remember, as that light ray comes in, one more thing, when I set this up, I wasn't taking into account the change between air and water, because we were only interested in this change down here between water and the solid. Okay, so there would be some refraction here that I didn't include in the picture. But anyways, just remember that as your light ray comes in, if it slows down, it gets closer to the perpendicular. If it were to speed up, it would get farther away from the perpendicular. Okay. So that's kind of a quick overview of reflection, refraction, Snell's law. Thanks.